Welcome to Chapter 9. In this lesson, we are going to talk about chi-square tests for goodness of fit. After this section, you're going to be able to state an appropriate hypothesis and compute expected counts for a chi-square goodness of fit test, calculate the chi-square statistics, the degrees of freedom, and the p-value for a chi-square test for goodness of fit, perform a chi-square test for goodness of fit, and conduct a follow-up analysis when the results of a chi-square test are statistically significant. All right, so in this section, we're going to start to discuss something called the chi-square goodness of fit test. This lesson is different in the other tests that we've talked about, and in this section, we're talking about categorical data. So remember, categorical data, we can't necessarily find the mean or the proportion or the average. Mathematical analysis does not make sense in it. We're putting information into categories: favorite color, favorite music, something like that. And your calculator in this section is actually going to do most of the work for you. So sometimes we want to examine the distribution of a single categorical variable. The chi-square goodness of fit test allows us to determine whether or not a distribution is valid. We're going to talk about what this means. Basically, it's saying if we claim that in an M&M box, there's going to be a certain percentage of each color. When I open up the M&M box, is there actually that same percentage of each color in each category? So let's take a look at the first example. If Mars on average, the mix of colors of M&Ms and milk chocolate candies will contain 13% of browns and reds, 14% of yellows, 16% greens, 20% oranges, and 24% blues. If we open up a bag of M&Ms, how do the proportions compare? Are they what they should be? Is what Mars says is true. Okay, so this is what Mars claims that each of the percentage colors are. So if we go purchase a bag of M&Ms, are we going to get 13% brown and reds, 14% yellows, 16% greens, and 20% oranges, and 24% blues? We will often organize our data in a one-way table to determine if what is hypothesized to be true is actually true. A one-way table displays only the distribution of one categorical variable in the sample. So basically, in simple language, this just means that we're going to have one row. So in this case, it would be color, and then your row would be the various colors, and that's it. So a chi-square goodness of fit test only deals with one row of data. Now, there's a new notation for this, all right? You're going to be looking at a chi-square. It's going to look like a curvy X, all right? Now, this is actually different than x squared. X squared means a number times itself. All right, so this capital curvy X is your chi-square statistic, and you just want to make sure that you use this notation correctly. So your chi-square statistic is going to kind of look like this. Okay, it's a capital curvy X, which is different than x squared. Let's take a look at a first example. So we already talked about on the previous page what Mars claims that the distribution of their colors are in a bag of M&Ms. So they claim that they're going to be 13% of browns and reds in every bag, 14% of yellows, 16% of greens, 20% of oranges, and 24% of blues. Now we could graph this on a histogram because this would allow us to see the distribution of the data. Okay, so I just want you to understand what distribution is. If you were going to look at the graph, you know, how high would the bars be for each category? So the one-way table below here summarizes the data from a sample bag of M&Ms. So we went out, purchased a sample bag of M&Ms, and then we figured out the proportion or the number of blue, the number of orange, the number of green, the number of yellow, red, and brown, okay? And we could figure out the percentages because we had a total of 60 M&Ms here, and we could figure out what percentage were blue. So you could just take 9 divided by 60, and then you could take 8 divided by 60 and 12 divided by 60, and that would give you the percentage of each category. Okay, now what our goal is here is the chi-square goodness of fit test tells us if the distribution of our sample matches the distribution that the company claims. So how good does our sample fit? So it's called a goodness of fit test because we're checking to see how well does the sample match what the claim is from the company or from our population. Okay, now, so for example, here, the sample proportion of blue M&Ms was 15%. So if this one was 15%, how does that compare to what it should be? So at the top, we said it should be 24% blues. So if you were going to graph this, think about right next to each other, the blue from my sample would be at 15 and the blue from the population would be at 24. Okay, so the distributions for that one actually look a little bit different. So overall, if I were to graph this, would the distributions look the same or different? Okay, so let's just take a look at how we can do a hypothesis test for this. Now, since the company claims that 24% of all M&Ms of milk chocolate candies are blue, we might think that something's going on because when we did this, we got the fact that there was 15%. The company says, hey, there should be 24%. Now, we could use a one sample z-test for proportions to test the hypothesis for your blue candy to say, hey, is the proportion, the company says the proportion of blue candy is 24%, but we say, we actually think it's a little bit different. Then what you'd have to do is you'd have to do a test of significance every single time for all of the rest of the colors. That's a lot of work. We want to avoid that if possible, okay? So that's going to take a lot of time. What the chi-square goodness of test allows us to do is it allows us to compare all of the proportions from the sample to the population all at one time. One test, not as much work required. So let's see what this chi-square test looks like. So we're assuming that the color distribution stated by Mars is true. That in fact 24% of all M&M milk chocolate candies are actually blue. For a random sample of 24 candies, the average number of blue candies should be 14.4. Okay, that number that we just found is called our expected count. Okay, where'd that come from again? So Mars Company said that 24%, so what the company said was they said, hey, 24% of our candies should be blue. And we said, okay, well, so if we take 60 candies, and I don't even actually count how many are in the bag, if I just take 60 candies and I want to figure out how many should I get, I'm going to take 24% times 60, and when I open up my bag and count them, I should get 14.4 blue candies. Okay, that's what I should get. That's what I expect to get. Now, we can use this method to find the expected counts for all of the other categories. So if you notice here, okay, we're multiplying them all by 60 because in our bag of M&Ms, there was 60. So this is what the company said we should get. Out of orange, we should get 20%, so 20% times 60 is 12. Green, we should get 16. 16% times 60 is 9.6. Okay, the company said we should get 14, so if I open up a bag of 60, 14% times 60 is 8.4. And I could keep going with this, all right? So, and then we also had our blue, which we said was 0.24 times 60. And we should have gotten 14.4 of those, okay? Now, we're going to compare the observed versus the expected. So the expected right here is what you got from multiplying what the percentage the company gets times how many were in your sample. So that's without opening the bag. The observed comes sort of second, right? So you can figure out the expected first. The observed comes second, and then you say, let's open up that bag of M&Ms and count and see, Are they the same? Do they match? So I should have gotten 14, but I got 9. I should have gotten 12 orange, but I got 8. I should have gotten 9.6, but I got 12 green. I should have gotten 8.4 yellow, but I got 15. I should have gotten 7.8 red, but I got 10. And then I should have gotten 7.8 brown, but I only got 6. So the chi-square statistic is going to tell us, did we get what we should have gotten? Does the observed values match what we got from the expected values? Okay, so if we take a look right here, let's take a look at this table and compare what they should be. So what should the counts be are called your expected counts. That's what you're expected to get, okay, whenever you open up that bag of M&Ms. So this is what the company claims. Okay, your company is claiming to get that certain percentage. All right, your observed count is how many you actually counted. So you counted 9, 8, 12, 15, 10, 6, okay? And then you had a total of 60. So how can we figure out the proportion to see if they match? So we already talked about this. We just did 9 divided by 60 is my total, 15%, 8 divided by 60, 0.13%. So there's sort of two ways we can compare this. We can compare the counts. I observed 9, I should have gotten 14.4, or I should have gotten 15%, or I should have gotten 24% and I actually got 15%. I should have gotten 20% orange, but I only got 13% orange. So a chi-square test is going to compare those observed versus the expected and say, are they off or are they good to go? Okay, now what I want you to keep in mind here is this is tricky. We are not measuring a quantitative variable here. So I understand that the percents are there, but the percents are representing a count, not something you can mathematically average. So think about those proportions. If you add them together and find the average proportion, well, what does that give you? That the average color of green? That doesn't really make sense, okay? So we're measuring the observed counts of the color to see if they match the expected counts. So we're looking at counts, not like something mathematically that we can just do. Okay, so how do you calculate the expected counts for a chi-square goodness of fit test? So we actually kind of already went over this. You're going to multiply the sample size by the expected proportion to get the expected count for each column. So all that means is you're going to get your sample, okay, and you're going to take n, which is your total sample size, and you're going to multiply it by p, which is the proportion for each individual value. So we just took like 24% times 60 to get how many should be blue. Now, I know this seems a little crazy, but do not round the expected counts. All right, I know that the expected counts turn out to be like 14.4. You can't have 0.4 of an M&M. But if you don't round your expected counts, your sample will not add up to the total. So if you do take a look at this previous page, now these expected counts, 14.4, 9.6, but when you add all of those together, okay, those are all going to give you 60, which needs to match the total observed. So just be careful with that. Okay, now I just went over this. So that notice the M&Ms on the example were 60, which is the amount in the bag, and the expected counts also add up to 60. The next thing we're going to talk about is a chi-square goodness of fit test. So this is a new statistic that we're going to be talking about. We're going to be comparing the distribution. So basically we're saying, okay, if I were to look at the distributions, here's distribution 1, and I were to look at the second distribution, okay, do they look the same or different? So if this is my observed and this is my expected, are they equal or are they not equal? Is something wacky with them? Okay, so what you're going to do is you're checking to see if we're comparing the observed counts to the expected counts. So our null hypothesis here is not any different than what we've talked about, right? So we always say the null is that there's no difference. There's no difference between the observed counts and the expected counts. The alternative hypothesis is different. It's always going to be the same. It's that there is a difference between the observed counts and the expected counts. It's always two-sided and always in terms of the population. Not every count has to be different. It's just saying if I look at all of these, maybe just